This talk I'll present Tamer, a system we have developed to control in fine-grained way the energy expenditure due to background activities in Android applications. This work is a collaboration with Justin Cappos from New York University. He's also in the audience, and Rodrigo Fonseca from Brown University. So does this screen look familiar to you? Imagine the last time your smartphone was about to die. There was no charging spot nearby, and you wish your battery would last longer. This problem keeps haunting us. The technology inside our phones and tablets has vastly improved, but the battery capacity hasn't followed the same pace. Battery decreases proportionally to the rate it's used. For apps that are in the foreground, there is a perceivable connection and expectation between usage and energy decay. If we spend too much time playing a game, browsing, or making a phone call, we'll notice that the battery is quickly draining. We as users also expect that when smartphones are in our pockets and our tablets are laying on the nightstand, little battery will be consumed. In many cases, this expectation is not met. Periodic background activities wake up the system to attend external events. Your device may wake up to check for new mails or synchronize its calendar. Energy bugs make things worse by preventing the system from switching to low power mode. Most importantly, in both cases, users don't know the cause, but feel the impact on their battery meter. So to understand how background activities affect the battery lifetime, we run a very simple experiment considering two scenarios. In the first, we have a device running a stripped version of Android open source project. We call here pure OSP. You can see a very limited choice of applications. We also consider a second scenario using the same phone in which we added Google Mobile Services, a collection of closed source applications from Google that improves the user experience. This package includes common applications like Instant Messenger, social network, navigation service, app stores, among others. The home screen of your smartphone or tablet probably resembles the picture on the right side. So we took these two phones, turned off their screen, and set them aside, waiting for battery depletion. We repeated the experiment for 4 devices. And here showed 2 of them. The battery depletion for the stripped version of Android is in red, whereas Google Mobile Services is in dark blue. We see a sharp decrease of battery lifetime once we install Google Mobile Services. For our Asus tablet, this reduction was of almost 200 hours. Again, both devices were left idling during the whole experiment. We proceeded to investigate the causes of this discrepancy. So we hooked the power monitor to the battery of a Galaxy Nexus phone. What I'm going to show here is a snapshot of these measurements. So here's what we found. The green chart shows the system's power draw over time for the stripped version of Android. Through some instrumentation described later, we also obtained a timeline of application event calls, which is stacked in a line at the top of the power timeline. For AOSP, we see that not much has happened. The power draw over time is mostly close to 0. There is a single power peak associated with one event. Now, in the case of Google Mobile Services, we see a surge of events happening periodically and raise the power draw sometimes up to 3 watts. I'm not expecting you to understand what these event acronyms mean. The main point here is that the number of events over the same period has dramatically increased. We traced these events and discovered they mostly originated from the Google package. So we have an issue here. These system wake-up sources are not visible without tracing or power monitoring. They are not initiated by users. And most importantly, they take a toll on the battery. What can we do to control this sudden increase of events? We have a few options. The first is reconfigure the frequency of background events for each application. The problem here is that only a few of these apps provide such control. We could uninstall or switch to alternative apps if they exist. Uninstall is not always possible, as some apps come pre-installed in our phone and we cannot remove them. Or for switching, we might feel locked to a particular app because of its functionality, ease of use, or popularity. For example, convincing my friends to switch from Instant Messenger A to Instant Messenger B is not an easy task. We can quit the app, and this is what many task killers promise to automate. It turns out some of these apps will just restart, and this might aggravate the battery problem, because now the app has to be loaded from storage. And finally, we can change system-wide settings to curb some of the background activities. This is a true coarse-grained solution. Many apps won't work anymore because we have a binary all or nothing switch. Ideally, what we want is a per-app controller that is more flexible. So observing all these limitations, we developed Tamer, a flexible event limiting mechanism for the Android operating system. Tamer provides fine-grained control over bad behavior of applications while trying to keep their functionality. So before I delve into the internals of Tamer, let's take a look at what types of background activities or events we're trying to control. So it turns out that Android has a very well-defined and narrow interface that allows developers to wake up the system and resume activities or even interject the execution of other applications that are in the foreground. One example is services. Developers can use services to offload side operations that are independent of the user interface. For example, weather forecast app defines a service asking the system to fetch tomorrow's temperature from the web. The system then responds with the requested data. Alarms are similar to service calls, but can be used to schedule periodic tasks at specific times. Application can use intent receivers to subscribe to events and later react once a notification arrives. An important component that weaves everything together are wake locks. To save energy, the system switches to low power mode as its default state. The wake lock API helps prevent the system from going to low power mode. For example, a developer on e-book reader would ask the screen to remain on while it's in the foreground. In addition, the Android framework also uses wake locks internally to guarantee that the system remains awake during the execution of callbacks from services, alarms, and intent receivers. So an important characteristic of these background event types is their asynchronicity. Android decouples the scheduling of an event from the execution of its callback. Therefore, the system can remain dormant until the execution of the event payload. The main insight in Tamer is very simple. If the event callback does not happen, applications will remain asleep as if nothing happened. For wake locks, we have symmetric calls to acquire and release a blocking object. So in this case, system state can be reverted. It's important to note that other Java primitives like threads or futures, along with Android-specific flavors of concurrency tasks, only work when the application is active in the foreground. While in the background, applications can only resort to the interface I'm showing here to wake up the system and regain CPU time. And this is the interface that Tamer acts upon. Now that we know which events we want to control, let's see how we can control them. I'm going to use an end-to-end example to identify the information necessary to rate limit events. We artificially rate limit events through selective blocking. So later I'll generalize this example and abstract the components of our controller. So let's take a look at what happens during a service dispatch call. As a developer, I first define the contents of the callback. In the case of a weather forecast app, we define a service to fetch the temperature. So fetch temperature becomes the event identifier. Once we have defined, we request a service call. The service runs asynchronously. And this request starts a series of function calls, as you can see on the right side. Between these calls, the system can go to sleep and later wake up. The callback is finally dispatched, and this is where the service starts running. So now that we know exactly when the system actually runs, we can prevent the event continuation. To block this event, we cut the wire, and if necessary, we restore the system state modified by the call graph. So let's transform this service example into a more general concept. Controller in Tamer can be seen as a logical component responsible for modifying the occurrence rate of background events. The logic component comprises three subunits: the observer, the arbiter, and the actuator. So the observer monitors and calculates at runtime the frequency at which calls to each event are made. In our example, when the fetch temperature service is dispatched, the observer updates the statistics for the weather application. The arbiter is the main part of our controller. It reads a policy defining how often a background wake-up should occur. At an event call, the arbiter checks the monitor rate against the threshold rate from the policy and advises the system on the next action. In the ideal case, we envision users telling Tamer how they want their apps to behave through a friendly interface. Well, this work focuses mostly on the controller mechanism. Therefore, at its current state, Tamer only fits the needs of experts, like developers and power users who write policies directly to the system. Finally, the actuator is responsible for discarding the event continuation in case the arbiter decides that the fetch temperature wakes up the system too often. So Tamer is made of 4 of these logical components, one for each type of background event. Tamer sits between applications and the Android application framework interface. The lower levels of the operating system are oblivious to Tamer. So we implemented each controller using Java code injection at runtime. This is possible thanks to the Xpose toolset. Xpose has the power to intercept functions inside the Android framework, sideload extra code, and trampoline between function calls. We use this mechanism to install the controller for each background event. So going back to our service call example, we know where our instrumentation point is in the function call graph, and that's where we install our controller code. The controller reads the policy, and if it realizes that the event dispatch should not proceed, it forces the original function call to return early. Finally, policies are written separately using the JSON format. So Tamer does not require any drastic system modification. We compiled our controllers using the Xpose API and distributed them as an Android package file. It installs just like any other application. We can modify the behavior of the applications without need for reinstalling or recompiling them. Tamer is compatible with customized Android releases from different vendors and also works with different generations of Android operating system. One caveat of our system is the need for rooting. We need privileged access to the internals of Android framework in order to modify them. So let's see how we can apply Tamer to real scenarios. In our evaluation, we consider 4 devices, 2 smartphones and 2 tablets. They comprise in different generations from 2011 to 2014. All of them running the Android KitKat OS. In the paper, we elaborate on how Tamer can be used in a series of situations. We first consider the impact of well-crafted policy for background events on the general lifetime of devices. Second, we illustrate how Tamer can be used to mitigate energy bugs in various applications. And finally, we talk about how we can throttle the GPS sensor using a single policy that fits different kinds of location-based applications. So for time reasons, I'll only cover the general lifetime case on 2 devices and one example of energy bug mitigation. So for the general lifetime scenario, let's revisit our motivating example and see how we can improve it. So this is the graph I showed in the beginning of this talk. We have a lifetime gap between AOSP and Google Mobile Services. We want to equip the extra functionality to Google Apps, but without the burden of losing many hours of battery life. What kind of policy can we write? So we resorted to Tamer's monitor to collect and investigate the frequency of events generated by the Google package. The table I show here ranks the top events in terms of calls and dispatches. For wake locks, we also considered or collected how long they kept the system awake. So from this table, we can tell, for instance, that the NLP, or Network Location Provider wake lock, had on average 1 acquire per minute over a monitoring period of 100 hours. In addition, NLP collector wake lock, which is a correlated event, held the system awake for more than 11 hours. The Network Location Provider functionality collects information about your device, location in the background, and from time to time ships it to Google. The problem here is that it's too frequent, especially when you are, for example, standing. So looking at this, we wrote 2 different policies that limit the occurrence of each event in this table. The first policy allows 1 call every 15 minutes. The second policy is more aggressive and allows 1 call every 45 minutes. The selection of these parameters is a subjective matter. So these policies are only applied when the system is in the background. So once again, here's our original graph. And this is what we got. We were able to restore a great deal of the lost battery hours. More importantly, because the events in question take place in the background, we did not notice any major difference in terms of functionality. So switching gears, just show how we can use Tamer to mitigate energy bugs caused by software errors. Energy bugs occur when the system is kept awake or when it shouldn't, and occur mostly due to unintended programming mistakes. But they can also be used for malicious purposes. Let's take the example of Bejeweled Glitz, a popular puzzle game available at the Google Play Store. So we discovered an energy bug while simulating a quick game session. During the session, Tamer's monitor indicated that one of the game's wake lock, audio in, was held. We turned the screen off, therefore switching the game to the background. We expected the audio wake lock to be released before the system became inactive. But to our surprise, it remained acquired, even though the audio interface was not being used anymore. So here you can see the effect of this programming blunder. During a period of only 12 hours, as shown by the red curve, our full battery went down to less than 45%. For comparison purposes, we measured the battery drop of a game session Candy Crush Saga, which has a very similar functionality to Bejeweled. The blue curve shows what should be our expectation in terms of battery life. For this experiment, the screen and the internet connection were kept off all the time. So on the right-hand side, we see the CPU state residency distribution while running Bejeweled. Although we expect the CPU to be in a deep sleep state during backgrounding, The held wake lock kept the CPU awake for most of the time, switching between different frequencies. So our next step was to write a policy to curb this unwanted behavior. On the right-hand side, we can see this policy. We declare the target application, the event type, in our case a wake lock, its name, and how often the system should allow its continuation. A 0 value tells that the wake lock acquired should be avoided at all costs. Finally, we tell the system that throttling should only take place when the application is relayed to the background. We repeated the measurements using this policy, and here are the improvements. On the left side, we see that the battery has dropped only 10% from its full capacity. Here, the green curve, which better matches our expectations. On the right side, we can see that with dismissal of the wake lock, the CPU remained deep sleep for more than 95% of the time. So this work focuses mostly on the controller part of Tamer, although we have only scratched the surface regarding policy definition. One challenge we face is how to define good policies. So far, I used the frequency of events as an heuristic to select our initial targets for rate limiting. This is far from perfect and can lead to problems if you're not careful and decide to block events which are essential to system functioning. So we lack tools that can quantify functionality changes to help us filter what can be blocked and what cannot be blocked. So the second challenge here is how to engage users in writing policies. As I said before, experts write policies directly using JSON files. But we want a more friendly way for users to express their desires. We need tools that help users visualize and understand what is causing the battery to drain quickly so that they can act and ask for changes. These are also open challenges. And finally, we have used event blocking to artificially reduce the call rate of events. Delaying batching the execution of multiple events at once is an alternative that can perhaps save more energy. But one particular challenge here is to identify what can be delayed and what cannot. So just to recapitulate, we saw that smartphone and tablet apps not only spend energy when active, but can also impact battery lifetime, especially when we least expect it. So if not controlled, background events can shave off many hours of user interaction. I presented Tamer, a tool to monitor and rate limit the occurrence of these events. Tamer modifies system behavior through policies that target specific applications. More importantly, it works without need of reinstalling or recompiling your favorite applications. And that's it. Thank you.
Max Altenstahl, Google. What about just the normal person solution of, say, put it in airplane mode, put it back? Did you compare to sort of simpler alternatives to help me save my battery so processes aren't doing things that I don't want them to do?
That's a good question. What about alternatives? One thing we noticed is that considering, as you said, normal users, they want their applications to function, say Google Now, and which needs an internet connection and things like that. And therefore, because, for example, airplane mode is very coarse-grained in that you turn off everything and you lose the functionality you want, we decided that maybe let's try something that we can affect a single application and rate limit what is perhaps like consuming too much energy. But I mean, quantitatively, we don't have that kind of comparison, what we can save and what cannot. But we're looking more at the functionality part. So users that want to keep their functionality in the background, but at the same time are worried about the battery lifetime.
Hey, Shazan from Ernst & Young. So question for you, for functionality, you said that it can break functionality in certain cases, so that's a limitation.
Indeed.
So, because I guess you're breaking the process, right? You're stopping the process, has to be restarted when the application comes back up?
Not really. Basically, what we're just trying to do, we don't break processes, it keeps running. We just discard the event continuation. Say you schedule a service call or alarm to occur, say, in 15 minutes from now. And basically, we just prevent that thing from continuing. So the alarm won't show up in 15 minutes. But the application keeps running as if it's, as I said, because it's asynchronous, there's no crashing, there's nothing happening, because the application should be ready to not receive that event.
Right.
Is a synchronicity.
So as part of breaking functionality, in the research you did, is there a way to understand which processes you shouldn't affect and which ones you should? Because I know you don't know until you know.
Indeed.
So as part of that, was there something you guys learned that there's as part of this application, you could have a better idea what to affect and what not to affect?
Right. It's a very interesting challenge to discover what can be broken, what cannot be broken. Because there are things that it might matter to some users and others might not. So the two policies I showed to you, like 15 minutes and 45 minutes. If I'm perhaps like jogging and maybe I want to keep my location tracking, 15 minutes to 45 minutes is too much, right? And perhaps in that case, you need a more fine-grained policy.
Right.
Now, with looking more generally speaking, it's right now, as I said, it's kind of a trial and error game because we don't have tools that can quantify how we can measure functionality to break it.
Right. Okay. Thank you.
No problem.
Yeah. Before you ask a second one, I want to ask it first.
Sure.
So, and it's actually a follow-on to what you just said. So, I was thinking about my canonical example of something that bothers me with my battery life is the GPS, where I need to have it on for certain things like Google Inbox to defer something until I get to a different location. But I really don't need it on all the rest of the time. And
right.
So it should be sampling much less often unless I'm in a car and it really needs to know exactly where I am. Have you looked into that kind of fine-grained tuning where it's sometimes on, sometimes off?
Yes, we have done that. I didn't cover it here, but in the paper we consider exactly the GPS throttling example. But we could actually work on the localization system and provide a controller specific for GPS throttling. And we could actually work with different applications, say Google Maps, or we had like a jogging application that tracks you on the map. We were able to use that to actually, consider, hey, we're running, we're inside the car, and then we can actually conceive different policies that can rate limit to the, the way that the GPS checks for new location positions.
What impact does Tamer have on the battery itself?
Tamer, Tamer, yeah, that's a very good question. Tamer, so we consider Tamer as it follows the execution flow of the application. So Tamer, through the expose, expose replaces the application scheduler. So when the application scheduler realizes that something else that needs to be run, and Tamer, what it does is just takes that or hooks into the system in order to block or read a policy or just let the event continue. So because Tamer does not use any of these, it doesn't run the active. It's not calling the system, but it's following what the scheduler is doing. And it actually freeloads the occurrence of events. So other events wake up the system for, say, I'm going to dispatch a service, I'm going to do an alarm thing. So in that sense, Tamer freeloads everything. And you could say, well, there's a very limited, we didn't measure it, but because we're freeloading things from the operating system that should occur already, I would say, well, the energy impact is negligible.
We have time for one more question if anybody wants to jump up. All right, let's thank the speaker.
Thank you.